I'm Yangchun. Today I'm going to present our work, HyperShell, a practical hypervisor layer gets OS cell for automated in VM management. This is a joint work with my colleague Junyuan and my advisor, Dr. Zhiqiang. Virtualization has been widely used in cloud computing. Here, I show a typical scenario of where machine running on the cloud. Today, data center usually host tens of thousands of virtual machines. And with more and more machines running on the cloud, and there is a need to have an automated way for in-VM management. Typically, to manage the OS, you have two approaches. The first approach is you own the machine, you can directly start a cell and run your major utility. And obviously, this approach is not practical for in a large scale in VM management. And moreover, you need to install, update, and execute the major utility in each VM. And it's really scattered and distributed. And another approach is to use SH to manage your OS remotely. And this approach enables centralized management and has better automation. And however, it still has limitation. First, you need to have the password to log in the system. And suppose you are managing thousands of VM. It's really painful to maintain all these passwords. Second, you need to install the major utility in each VM. Whenever there is an update for the utility, you need to update all of them in each VM. So can we move all these major utilities and out of VM to the virtualization layer so that we can manage the guest OS on the virtual machine monitor layer? This is doable, as I'm going to talk about today of our work, HyperShell. And with this approach, there are several advantages. First, you only need to install the major utility at the hypervisor layer now. And this enables an automated, uniform, and centralized guest OS management. And unfortunately, this approach is non-trivial. The challenge is the semantic gap problem. Typically, all the below OS approach need to address this semantic gap problem. And before describing how we solve this challenge, I would like to first revisit how an EVM program executes. Suppose you are going to get the machine land on the running OS. You can use the hostname bin utility, hostname utility to get the hostname. And here on the left figure, I show the Syscall tray for this hostname. In total, there are 41 Syscall calls, and as you can see, it's the uland that actually returns the hostname. And on the right figure, I also show how uland try to traverse the kernel data structure to get the machine name. So if we try to use a manual approach to bridge the semantic gap, we need to do as uname do. It's really tedious. And since the system call is the only interface to request OS servers, and they are often trusted, so why not reuse this system call and let the hypervisor program directly use this system call from the guest.os. And with this idea, we introduced the reverse system call execution. And we demonstrate our approach on the Linux operating system and KVM hypervisor. Here is our architecture. And basically, a KVM virtualization-based system, there are two kinds of systems. One is the guest OS, which runs on top of KVM hypervisor, and the host OS, which provides the virtualized resource to the KVM. And our idea is to separate the execution of management utility into two parts. All the user space code is running on the host OS. And in the same time, we also select something called to execute on the guest OS. And our reverse system call execution works like an upper call, and the system call is not triggered on the guest OS user space. Instead, we inject the system call from hypervisor and run it on the guest OS. Next, I will detail the design of each component of our system. First, let us see the host OS design. Since our key approach is to redirect the system call for execution, the first question is how to intercept the system call. We have adopted a library interpretation approach, and this approach requires no modification to the native program. Basically, we detour the system call from the glibc to our system call patcher, and our system call patcher will decide the system call either to run on the host OS or on the guest OS. So we need to define our system call execution policy. To see this policy, let's revisit the system call trace of our host LAN again. Basically, we divided the system call into two sets. The first set of system call are much clearer. And for instance, like the system call highlights here, they are related to the process creation, memory allocation, or process cleanup. And this system call must run on the host OS. And there are also system calls related to output the result to the host screen and host file. Because we want to see the result of the program, so these system calls are also running on the host. Then, for other system calls, they are related to the inspection of this program. Like the ULAM here, they must run on the guest side. And however, there are some system calls is not always clear. For instance, suppose you want to copy the password file, the etc shadow file from the guest to the host. And here we show the system call trace again. As you can see, some file system related system call run on the host side, but some are run on the guest side. These system calls are not independent, they are related. As you can see, this system call has dependency on the file descriptor. So if we open a shadow file on the guest OS side, and he returns a 0 file descriptor, then the following system call which is operating on this file descriptor and also need to run on the guest OS. So how can we differentiate the file descriptor from the guest or from the host? Our solution is to use the file descriptor itself. As the file descriptor is just an index to the open file in the kernel for each process, it has a limited maximum value. So we can actually use the higher bit of the file descriptor as a flag to differentiate it. Then it turns to the design of the guest OS side. As the system call must run on certain execution content on the guest VM. So our idea is to create a helper process for this purpose. And this helper process should have higher privilege so that all the system can be run correctly. And the challenges come to how can we create this helper process, as we are not logged in the system to run the process. As we are able to inject the system call, so we can actually find a process which has high privilege and inject a fork system call to create a trial process as our helper process. Then there another question comes out. Before we create our helper process, how can we inject the system call for execution, or when it's safe to inject the system call? And normally, the program is running either on the user space or the kernel space, and it is safe to execute a system call on the user space, but it is not the case for kernel space. For instance, if we inject a system call when the OS is running on the interrupt content, we may make the system inconsistent or even crash. So our idea is to inject the system call right before entering the kernel space or right returning to the user space. Let us take a look at the HyperShell overview to see how it actually works. First, we will create our helper process and run our management utility, let's say the ls here, and we will intercept all the system call. And if the system call need to redirect to the guest VM for execute, we will set up the argument and inform the guest VM. And this ls will wait for the result. And the guest VM will also wait for the OS trap to the hypervisor and inject the system call, run it, and update the related buffer. And finally, the guest VM will inform the host OS side, and the LS will copy back the result and resume execution. And that is how HyperShell works. And next, I want to talk about the evaluation result. First, we want to verify whether the HyperShell can actually support native utility to run transparently. And we have selected 101 utilities from 6 Linux packages. And we verify that all these utilities run correctly. And in terms of performance overhead, HyperShell introduced 2.7 times slowdown compared to a program running in native KVM. And we also evaluate the impact on the guest VM. And here we evaluate two phases. The RI phase, which is to create the helper process. And the RE phase is where system call is running on the helper process context. And we have first select the LI bench to quantify the primitive slowdown. As you can see, the RI phase has a large slowdown. But because RI phase only runs only run once, and will finish once the HyperShell finishes. And for RE phase, the slowdown is small. This is because we only trap the system call on the helper process context. And we also select for real-world workload to quantify the performance overhead. And as you can see, for the IA phase, the slowdown is also large, and the IE phase, the slowdown is also small. In the following, I will demonstrate an interesting use case of our system. With HyperShell, we can actually run some antivirus software to scan the files in the guest OS, even this image is encrypted. Here is our experience setup, and we put 2 wires in this file, and then we run the client AV to scan this to run on the HyperShell and scan the guest OS, and we successfully detect 2 viruses. And we also compare our work to other work. They are most of these work are about virtual machine introspection. You can refer to a paper for detailed comparison. Next, I want to discuss the limitation and future work. HyperShell will bypass all the existing user login assistant. So we can add a new logger to record this event at the hypervisor layer. And HyperShell requires the trust of guest OS. So it cannot be used for security critical application unless special care is taken for this code. And finally, HyperShell requires both OS running in the host OS and VM to have compatible Syscall interface. And so one idea is to perform additional Syscall translation so that we can able to work for a larger set of OS. In conclusion, we talk about HyperShell, a practical approach for automatic, uniform, and centralized guest OS management. And it automatically bridges the semantic gaps through Syscall execution redirection. And thank you for your attention. Now I would like to take the question.
Hi, Tim Wood from George Washington University. I think this is interesting. I'm a little skeptical about some of the use cases for it, but one case that I think really could be useful is if you were to combine this with the first talk from this session about a library OS where your virtual machine doesn't have the ability to run any other processes. So have you thought about how this kind of system could be applied to something like their operating system where maybe you really need all of the management to be done outside of the VM itself?
I think the method is the same. We just need to identify and then redirect to the guest OS for execution. Because we know that the POSIX standard, if there's a POSIX standard, we just we just do obey this standard.
So Yang?
Yeah.
So one of the things that you showed overheads during the time when you're initializing the system and when you're running, injecting a command. But when you're not doing either of those things, when you're not monitoring the system, or when you're not using HyperShell to monitor the system, at that point, how much overhead is there?
Oh, there's no overhead.
I thought that was a pretty cool feature of the paper. You should advertise that more. That was
yeah, because we can enable this feature at home.